In linear algebra, the determinant is a useful value that can be computed from the elements of a square matrix. The determinant of a matrix A is denoted det, or A. In the case of a 2 times 2 matrix, the specific formula for the determinant is simply the upper left element times the lower right element, minus the product of the other two elements. Similarly, suppose we have a 3 times 3 matrix A, and we want the specific formula for its determinant, A. Each determinant of a 2 times 2 matrix in this equation is called the minor of the matrix A. The same sort of procedure can be used to find the determinant of a 4 times 4 matrix, the determinant of a 5 times 5 matrix, and so forth. Determinants occur throughout mathematics. For example, a matrix is often used to represent the coefficients in a system of linear equations, and the determinant can be used to solve those equations, although more efficient techniques are actually used, some of which are determinant revealing and consist of computationally effective ways of computing the determinant itself. The use of determinants in calculus includes the Jacobian determinant in the change of variables rule for integrals of functions of several variables. Determinants are also used to define the characteristic polynomial of a matrix, which is essential for eigenvalue problems in linear algebra. In analytical geometry, determinants express the signed n-dimensional volumes of n-dimensional parallelepipeds. Sometimes, determinants are used merely as a compact notation for expressions that would otherwise be unwieldy to write down. It can be proven that any matrix has a unique inverse if its determinant is non-zero. Various other theorems can be proved as well, including that the determinant of a product of matrices is always equal to the product of determinants, and the determinant of a Hermitian matrix is always real. Definition. There are various ways to define the determinant of a square matrix A, i.e., one with the same number of rows and columns. Perhaps the simplest way to express the determinant is by considering the elements in the top row and the respective minors, starting at the left. Multiply the element by the minor, then subtract the product of the next element and its minor, and alternate adding and subtracting such products until all elements in the top row have been exhausted. For example, here is the result for a 4 times 4 matrix. Another way to define the determinant is expressed in terms of the columns of the matrix. If we write an n times n matrix A in terms of its column vectors where the vectors are size n, then the determinant of A is defined so that where B and C are scalars, V is any vector of size n and I is the identity matrix of size n. These equations say that the determinant is a linear function of each column, that interchanging adjacent columns reverses the sign of the determinant, and that the determinant of the identity matrix is 1. These properties mean that the determinant is an alternating multilinear function of the columns that maps the identity matrix to the underlying unit scalar. These suffice to uniquely calculate the determinant of any square matrix, provided the underlying scalars form a field. The definition below shows that such a function exists, and it can be shown to be unique. Equivalently, the determinant can be expressed as a sum of products of entries of the matrix where each product has n terms and the coefficient of each product is -1 or 1 or 0 according to a given rule. It is a polynomial expression of the matrix entries. This expression grows rapidly with the size of the matrix, so it will first be given explicitly for the case of 2 times 2 matrices and 3 times 3 matrices, followed by the rule for arbitrary size matrices, which subsumes these two cases. Assume A is a square matrix with n rows and n columns, so that it can be written as the entries can be numbers or expressions. The definition of the determinant depends only on the fact that they can be added and multiplied together in a commutative manner. The determinant of A is denoted as det, or it can be denoted directly in terms of the matrix entries by writing enclosing bars instead of brackets. 2 times 2 matrices. The determinant of a 2 times 2 matrix is defined by if the matrix entries are real numbers. The matrix A can be used to represent two linear maps. One that maps the standard basis vectors to the rows of A, and one that maps them to the columns of A. In either case, the images of the basis vectors form a parallelogram that represents the image of the unit square under the mapping. The parallelogram defined by the rows of the above matrix is the one with vertices at and, as shown in the accompanying diagram. The absolute value of AD-BC is the area of the parallelogram, and thus represents the scale factor by which areas are transformed by A. The absolute value of the determinant together with the sign becomes the oriented area of the parallelogram. The oriented area is the same as the usual area, except that it is negative when the angle from the first to the second vector defining the parallelogram turns in a clockwise direction. To show that AD-BC is the signed area, one may consider a matrix containing two vectors A equals and B equals representing the parallelogram's sides. The signed area can be expressed as a, b, sin theta for the angle theta between the vectors, which is simply base times height, the length of one vector times the perpendicular component of the other. Due to the sign, this already is the signed area, yet it may be expressed more conveniently using the cosine of the complementary angle to a perpendicular vector, e.g., A equals, such that A, B, cos theta, which can be determined by the pattern of the scalar product to be equal to AD-BC. Thus the determinant gives the scaling factor and the orientation induced by the mapping represented by A. When the determinant is equal to 1, the linear mapping defined by the matrix is equiareal and orientation preserving. The object known as the bivector is related to these ideas. In 2D, it can be interpreted as an oriented plane segment formed by imagining two vectors each with origin and coordinates and the bivector magnitude is the signed area, which is also the determinant AD-BC. 3 times 3 matrices. The determinant of a 3 times 3 matrix is defined by the rule of Saris as a mnemonic for the 3 times 3 matrix determinant. The sum of the products of three diagonal northwest to southeast lines of matrix elements minus the sum of the products of three diagonal southwest to northeast lines of elements. When the copies of the first two columns of the matrix are written beside it as in the illustration. This scheme for calculating the determinant of a 3 times 3 matrix does not carry over into higher dimensions. N times n matrices. The determinant of a matrix of arbitrary size can be defined by the Leibniz formula or the Laplace formula. The Leibniz formula for the determinant of an n times n matrix A is here. The sum is computed over all permutations sigma of the set 1, 2, n. A permutation is a function that reorders this set of integers. The value in the ith position after the reordering sigma is denoted sigma I. For example, for n equals 3, the original sequence 1, 2, 3 might be reordered to sigma equals 2, 3, 1, with sigma 1 equals 2, sigma 2 equals 3, and sigma 3 equals 1. The set of all such permutations is denoted Sn. For each permutation sigma, Sgn denotes the signature of sigma, a value that is +1 whenever the reordering given by sigma can be achieved by successively interchanging two entries an even number of times, and -1 whenever it can be achieved by an odd number of such interchanges. In any of the summands, the term is notation for the product of the entries at positions, where I ranges from 1 to n. For example, the determinant of a 3 times 3 matrix A is Leibniz Vita symbol. It is sometimes useful to extend the Leibniz formula to a summation in which not only permutations, but all sequences of n indices in the range 1, n occur, ensuring that the contribution of a sequence will be 0 unless it denotes a permutation. Thus the totally antisymmetric Leibniz Vita symbol extends the signature of a permutation, by setting for any permutation sigma of n. and when no permutation sigma exists such that the determinant for an n times n matrix can then be expressed using an n-fold summation as or using two epsilon symbols as, where now each IR and each junior should be summed over 1. Properties of the determinant. The determinant has many properties. Some basic properties of determinants are where n is the n times n identity matrix. For square matrices A and B of equal size. For an n times n matrix, if A is a triangular matrix, i.e., Ij equals 0 whenever I greater than j, or, alternatively, whenever I less than j, then its determinant equals the product of the diagonal entries. This can be deduced from some of the properties below, but it follows most easily directly from the Leibniz formula, in which the identity permutation is the only one that gives a non-zero contribution. A number of additional properties relate to the effects on the determinant of changing particular rows or columns. Viewing an n times n matrix as being composed of n columns, the determinant is an n-linear function. This means that if one column of a matrix A is written as a sum V plus W of two column vectors, and all other columns are left unchanged, then the determinant of A is the sum of the determinants of the matrices obtained from A by replacing the column by V and then by W. If in a matrix, any row or column is 0, then the determinant of that particular matrix is 0. This n-linear function is in alternating form. This means that whenever two columns of a matrix are identical, or more generally some column can be expressed as a linear combination of the other columns, its determinant is 0. Properties 1, 7 and 9, which all follow from the Leibniz formula, completely characterize the determinant. In other words, the determinant is the unique function from n times n matrices to scalars that is n-linear alternating in the columns, and takes the value 1 for the identity matrix. To see this, it suffices to expand the determinant by multilinearity in the columns into a linear combination of determinants of matrices in which each column is a standard basis vector. These determinants are either 0 or else plus or minus 1, so the linear combination gives the expression above in terms of the Leibniz Formula symbol. While less technical in appearance, this characterization cannot entirely replace the Leibniz formula in defining the determinant, since without it the existence of an appropriate function is not clear. For matrices over non-commutative rings, properties 7 and 8 are incompatible for n2, so there is no good definition of the determinant in this setting. Property 2 above implies that properties for columns have their counterparts in terms of rows. Viewing an n times n matrix as being composed of n rows, the determinant is an n-linear function. This n-linear function is in alternating form. Whenever two rows of a matrix are identical, its determinant is 0. Interchanging any pair of columns or rows of a matrix multiplies its determinant by -1. This follows from properties 7 and 9. More generally, any permutation of the rows or columns multiplies the determinant by the sign of the permutation. By permutation, it is meant viewing each row as a vector and reordering the rows by interchange of Rj and Rk, where J, K are two indices chosen from 1 to n for an n times n square matrix. Adding a scalar multiple of one column to another column does not change the value of the determinant. This is a consequence of properties 7 and 8. By property 7, the determinant changes by a multiple of the determinant of a matrix with two equal columns, which determinant is 0 by property 8. Similarly, adding a scalar multiple of one row to another row leaves the determinant unchanged. Property 5 says that the determinant on n times n matrices is homogeneous of degree n. These properties can be used to facilitate the computation of determinants by simplifying the matrix to the point where the determinant can be determined immediately. Specifically, for matrices with coefficients in a field, properties 11 and 12 can be used to transform any matrix into a triangular matrix. whose determinant is given by property 6. This is essentially the method of Gaussian elimination. For example, the determinant of can be computed using the following matrices. Here, B is obtained from A by adding -1/2 times the first row to the second, so that det equals det. C is obtained from B by adding the first to the third row, so that det equals det. Finally, D is obtained from C by exchanging the second and third row, so that det equals -det. The determinant of the triangular matrix D is the product of its entries on the main diagonal. 2, 4.5 equals -18. Therefore, det equals -det equals +18. Multiplicativity in matrix groups. The determinant of a matrix product of square matrices equals the product of their determinants. Thus, the determinant is a multiplicative map. This property is a consequence of the characterization given above of the determinant as the unique n-linear alternating function of the columns with value 1 on the identity matrix. Since the function mnk that maps mdet can easily be seen to be n-linear and alternating in the columns of M, and takes the value det at the identity, the formula can be generalized to products of rectangular matrices, giving the Cauchy-Binet formula, which also provides an independent proof of the multiplicative property. The determinant det of a matrix A is non-zero if and only if A is invertible, or, yet another equivalent statement, if its rank equals the size of the matrix. If so, the determinant of the inverse matrix is given by, in particular, products and inverses of matrices with determinant 1 still have this property. Thus, the set of such matrices form a group known as the special linear group. More generally, the word special indicates the subgroup of another matrix group of matrices of determinant 1. Examples include the special orthogonal group and the special unitary group. Laplace's formula and the adjugate matrix. Laplace's formula expresses the determinant of a matrix in terms of its minors. The minor m, J is defined to be the determinant of the times matrix that results from A by removing the ith row and the jth column. The expression I plus m, J is known as cofactor. The determinant of A is given by calculating det by means of that formula is referred to as expanding the determinant along a row or column. For the example 3 times 3 matrix Laplace expansion along the second column yields. However, Laplace expansion is efficient for small matrices only. The adjugate matrix adjective is the transpose of the matrix consisting of the cofactors, i.e., in terms of the adjugate matrix. Laplace's expansion can be written as Sylvester's determinant theorem. Sylvester's determinant theorem states that for A, an m times n matrix, and B, an n times m matrix, where M and N are the m times m and n times n identity matrices, respectively. From this general result several consequences follow. For the case of column vector C and row vector R, each with m components, the formula allows quick calculation of the determinant of a matrix that differs from the identity matrix by a matrix of rank 1. More generally, for any invertible m times m matrix X, for a column and row vector as above.